To get started in this video, we are going to let R be a ring, S is going to be a subring of our ring R, and I is going to be an ideal of our ring R. And I want to draw a schematic picture here. R is up at the top, and R includes both I and S. And I is my ideal, and S is just a subring. And because I and S are subsets, I can look at their intersection, and S intersect I is going to live down here, where these lines are indicating the subset relations. I also want to recall a fact from a previous assignment. You have previously shown that the intersection of two subrings is a subring, and both I and S are subrings. And so we already know that S intersect I is a subring of the big ring R. And that is by a previous assignment. Now, the other thing that I want to point out is that R and I and S intersect I all use the same ring operations. They all use the ring operations for R. And since S intersect I is a subset of I, and S intersect I is a subset of S, and they're all rings, we also know that S intersect I is a subring of the ideal I, and S intersect I is a subring of the subring S. And in this particular video, I want to ask the question, can we say anything else about S intersect I? And in order to investigate that, I want to redraw the picture. So here is our picture from the previous page. And I want to consider this idea. Let's let little s be any element of the subring S. And I do want to remind myself that the subring S is a subset of the ring R. And so little s is also an element of the ring R. And I'm going to let little a be any element inside the intersection S intersect I. And that's going to imply that A belongs to S and A belongs to I. So now I want you to look at this. Let's just multiply A and S together. Now, A belongs to the subring S, and little s belongs to the subring S. So this particular product can be thought of as a product of two elements of the subring S. But since S is a subring, that will imply that AS has to belong to the subring S, since S is a subring. But now I want to kind of look at AS with a different kind of I. I know that A belongs to I, and S belongs to R, and I itself is an ideal. So A times S is now something in I times something inside R, and I is an ideal. That's enough to say, by the definition of ideal, that that product has to be inside I, since I is an ideal. And if I think about this statement here, and this statement here, those two statements together say that we have AS belongs to S intersect I, and that this is true for all little s inside the subring S, and all little a inside the intersection of S and I. Now, the same kind of argument can be made for SA. So, in the same way, we can show SA belongs to S intersect I. And if I think about this statement here and this statement here, since they are both true for all little s's in S and all little a's in S intersect I, those two things are enough to say that S intersect I is an ideal inside the ring S. And I want to formally state that as a lemma. So we have proved the following lemma. If we have this situation where this is a subring, this is a ring, and this is an ideal, then we know that S intersect I is an ideal of the ring S, and that actually says S mod S intersect I is then a quotient ring.